Okay, so I'm going to tell you a little bit about using NERSC resources for doing calculations in the standard model of nuclear and particle physics. And really the goal here is to try and understand the subatomic structure of the world around us from the underlying theory that we think describes it. So this theory is built from particles and forces, so it involves quarks, various different types of quarks, leptons like electrons and muons and neutrinos, and force-carrying particles called bosons that keep things together. And the big questions we really want to try and answer are: what is the structure of matter? How does it depend on the parameters in this standard model that's been written down? And how do we constrain this model in experiment? And how do we look for places where it doesn't describe things? So look for physics beyond the standard model. And there are places where we know that has to be the case. So for example, dark matter, dark energy, and the origin of neutrino masses are things that the standard model itself does not encompass. As well as the fundamental particles in this model, the standard model really also describes the emergence of complexity. So it describes things like protons, which are already extremely complicated objects, nuclei, and all the way up to neutron stars and supernovae. Well, of course, gravity is important. We'll talk about those as well. And in principle, the same physics is really describing everything going on at these different length scales. And for most of it, you can boil it down to about 5 parameters in the standard model that actually affect this. Of course, this is in principle, and actually calculating these things is an extreme challenge. So one of the pieces of the standard model is the strong interaction. It combines that with electromagnetism and the weak interactions. But the strong interaction is particularly important for what I want to talk about. And because this is the force that really binds the quarks and gluons inside protons into the composite objects like protons and those into nuclei. And an important part of this interaction is that it depends very strongly on the energy at which you're probing it. So the figure at the right shows the strength of the coupling between a quark and an antiquark in this theory as a function of the energy at which they're scattering. And at high energies, this is becomes quite small. It goes to 0 asymptotically, and means that you can do analytic calculations based on an expansion in that parameter. And that's really how we've, for many, many decades, been probing this theory and comparing to experiment, seeing that it describes what goes on. However, if you go to low energies, order 1 in this dimensionless plot here, you find that this coupling becomes large and there's no way you can do a perturbative calculation. And so you have to turn to numerical calculations, and the approach that's used is known as lattice QCD. So this is a tool with which to deal with the quarks and gluons, and really it provides a rigorous definition of the mathematical theory. And basically you formulate the problem as of computing some observable quantity O as writing down an integral over all of the quark and gluon degrees of freedom on some 3+1 dimensional spacetime. Of course, to work with that on a computer, you need to discretize it and compactify the system. And you end up, of course, with a finite number of degrees of freedom. For state-of-the-art lattice QCD calculations, that might be 10 to the 8th or 10 to the 12th. And in order to do that integral, you use important sampling Monte Carlo to choose the samples according to some particular probability distribution that's defined by the theory, and then you just average over them. Probably the most challenging part of this is to undo the harm that you've done in these steps. So the world is not discrete, the world is not finite in size, and statistics is always a challenge. And so solving this becomes a very large-scale numerical challenge, and something that NERSC has been very helpful for. So there's a lot of lattice QCD that goes on at NERSC, and so this is a list of the top users over time that I got from Steve Gottlieb, who got it from Richard. And as you can see, lattice QCD appears many times in this, as Richard mentioned last night as well. So what do we do with all that computing? So I want to tell you a little bit about some of the highlights of science that have come out in the last decade or so. So let me start talking about thermodynamics of the vacuum of this theory. So really the phase structure of this theory. And So this is really described by the equation of state, relations between pressure and density and things like this. And this is really important as it describes matter that we observe in various different places. So we can think about the early universe as it's expanding. We can think about neutron stars and neutron star mergers. So these are places where QCD is really a critical piece of the physics that's going on. And so this phase diagram at the right shows what happens as you change the temperature in the vertical axis and the densities in the horizontal axis. And there's really two densities here. One is called baryon density, and that's really thinking about protons plus neutrons. And the other is something called isospin density, which is, in a loose sense, protons minus neutrons. Okay, so a neutron star, of course, is predominantly neutrons and has some protons, so it's sitting somewhere out in this mu I, mu B plane. And nuclei as well are down in the bottom corner there. They're also things where the proton and neutron ratios are not one. So in order to understand these systems, we really want to probe this diagram. So experimentally and observationally, we get access to this through heavy ion experiments, and more recently through gravitational wave observations of neutron star mergers, for example. On the theory side, one thing we've learned over the last decade and a bit is really what's going on along this axis of zero density, so as a function of temperature. And lattice QCD calculations have really shown definitively that at a temperature of about 155 mega electron volts, you find a crossover transition from a phase of hadrons like protons and neutrons to something where the quarks and gluons are somewhat basically free. So a gas of quarks and gluons, or a plasma. More recently, we've also explored this other axis, so the isospin chemical potential axis, isospin density axis. And this is something where the plot at the bottom shows one of the thermodynamic quantities, which is the speed of sound in this medium. And these recent calculations have shown that the speed of sound turns over and approaches the asymptotic value of a third, which is what a free gas must do, from above. It's also been demonstrated that there is superconductivity in this system at large densities or chemical potentials, and the first determinations of the superconducting gap have been made. Interestingly, although what we really want to know about is somewhere out in this mu B, mu I plane on this plot here where neutron stars are, the calculations along this mu I axis itself can be used to put rigorous bounds on what the pressure, for example, is anywhere in this plane. Turning to a different topic, we also want to understand the standard model better and determine its parameters, as I mentioned at the start. And typically this is done by taking some quantity Q that we can measure in an experiment, for example, at the Large Hadron Collider. And that is generically something we can write in terms of some convolution of standard model parameters and things that we can calculate in lattice QCD. Right? Really, because the experiments see hadrons in their final state, that's what you have to deal with. So you need lattice QCD. And for many years, we've tried to constrain parameters by doing these experiments and calculations. And one important thing to try and do is to over-constrain the system. So to try to look for a discrepancy. And the plot at the right is known as the CKM unitarity triangle, where the angles and axes here correspond roughly to parameters in the model, and the different bands correspond to different experiments. And for example, the apex of that triangle is something where we try and see that there's disagreement between different extractions. We also want to look beyond the standard model. And in order to do that, you need to know what the standard model should predict for whatever quantity is you're trying to measure experimentally. And a nice example of this is the anomalous magnetic moment of the muon. This has been in the news recently, as there've been very precise new experimental measurements at Fermilab, and there've been theory calculations of this. So this plot is a little overpopulated, but basically Going back in time, you basically had the green band as the experimental result and the blue band as the theory expectation for this, and there was a big discrepancy between it. The theory was really not pure theory, it was making use of some other experiments. And with pure theory calculations of this, you actually end up with something like the red band here. And so this discrepancy between theory and experiment has basically gone away, although we need to wait until February next year until new experimental results out and additional theory calculations will come out that will most likely confirm that this is no longer a real discrepancy. Okay, so we can also try and understand the bound states of the theory. So hadrons are the bound states of quarks and gluons. And lattice QCD is able to reproduce the mass of things like the proton. And for me, that's also a very important kind of milestone in that it's demonstrating that QCD can describe the strong interaction at the energy scales where it's strongly interacting, as well as at very high energies. But with theoretical control, you can also go beyond what you can access experimentally. So, for example, you can separate the difference between the proton and neutron mass into its electromagnetic contributions and its quark mass difference contributions. But we can also make predictions for things that haven't been seen. So this is a figure showing a zoo of hadrons that contain more exotic charm and bottom quarks. These are cousins of the proton. Some of them have been seen in experiment. The little red bars correspond to experimental determinations, but many of them haven't. And lattice QCD is able to predict them, and some of these have been subsequently seen experimentally. There are also states that are not found in simple models that lattice QCD predicts. And this has been motivation for experiments such as the GluX experiment at Jefferson Lab that is really built to try and find exotic resonances like this pi1 resonance that this shows some phase shifts of. We also like to look at the internal structure of the bound states. So really to unravel how the quark and gluons turn into these bound states. For example, a simple question might be to ask, what is the charge and magnetism distributions within such a state? And from a more theoretical point of view, you really want to know where the quarks and gluons are inside the system. And the animation at the top right really shows an artistic impression of what's going on, sort of an artistic impression motivated by experimental results of what's going on inside of it. There are other quantities that we can look at, things related to how the object couples to gravity, for example. That tells you, of course, about its mass, but also how the spin of the quarks and gluons inside the state gives you the spin of the proton. And there've also been in recent years calculations of the pressure and shear force distributions that are inside. So understanding this structure is really a central goal of a big new facility in experimental nuclear physics. This is the electron-ion collider that will be built at Brookhaven National Lab and operational in the 2030s. And this is the highest priority from the 2023 long-range plan in nuclear science. And it's really designed to understand the structure of the proton and nuclei in unprecedented detail. And theory input, such as the calculations of those pressure distributions, is really important in designing and operating that experiment. Moving on to nuclei. Nuclei are much more complicated systems than even a proton, and they involve many energy scales. And they're computationally complex in at least two exponentially difficult ways. So these are things where we're not yet able to do really calculations that connect directly to the physical world. We use heavier than physical quark masses, and we haven't taken the limit of the lattice spacing going to zero. But first calculations have come out here for things like the magnetic moments of nuclei, and for nuclear processes such as the first nuclear reaction that went on in the universe, where a proton and neutron come together and form a deuteron and radiate a photon. And other processes such as the PP fusion process that powers the sun. So nuclei give us a laboratory for looking at important questions about the standard model, such as the symmetries that it obeys. So neutrinoless double beta decay, in which a nucleus of atomic number A and proton number Z, two neutrons in that system turn into protons, so the proton number goes up by 2, and 2 electrons come out. So this is a theorized process in which, if it happens, would mean that one of the symmetries of the standard model, lepton number, is in fact violated. And this will be important because it would tell you about the origin of the matter-antimatter asymmetry that we see in the universe. And this also experimentally is a high priority in the recent long-range plan. Understanding this theoretically is a little complicated because the models we use to deal with the nuclear physics in these decays have uncertainties that are very hard to quantify. And this is also a little complicated because these nuclei are things where we can't directly do lattice QCD calculations of them. They're too complex. So there's really no realistic hope that we'll be doing direct calculations. However, you can basically use a hierarchy of different theories in order to connect from the underlying standard model to something where you can make contact with the experiment. So using lattice QCD to look at few body systems where this process might happen, to connect to effective field theories and then connect to various many body methods, allow you basically to bootstrap your way up to being able to control uncertainties in these calculations rigorously. And just this year, we were able to do the first calculation of this 2 neutron to 2 proton transition matrix element in this system. Of course, this is not something that happens physically, but it's a piece that you can use to put into this effective field theory framework and then connect to many body methods. And it's really an open goal of the field is to take that pipeline and really connect it to the nuclei that are used in these experiments. Nuclei are also used at the so-called intensity frontier, and this is really DOE HEP jargon for experiments that use basically the large mass of a system and very intense beams in order to have cross-sections for things that don't happen very frequently. So for example, in neutrino physics, neutrinos very much like to travel through everything they can. And so in order to have an experiment where you're doing, studying neutrinos, you need a very intense beam and you need a lot of material. Similar for dark matter studies, looking for decays induced by dark matter hitting a nucleus is something where you need a lot of nuclei in order to see that. And so, for example, the LZ experiment that was measured yesterday is one of these cases where you have a large tank of nuclei and you're looking for a very, very rare process happening inside that tank. In order to really understand these experiments, they're made of nuclei, so you need to understand the QCD physics of these, of what's going on in order that you might actually be able to say something about beyond the standard model physics. So recently we've been looking at, the field has spent a lot of time looking at the weak current interactions between neutrinos and a nucleon, a proton or a neutron, and computing the form factors needed for the Dune experiment, and also doing first calculations of nuclear effects that might happen from it not being a single proton that you're scattering off. Okay, so let me move on and talk a little bit about challenges that the field has. And let me just say a little bit more about the details of calculations. So really you can think about lattice QCD calculations as broken up into 4 different steps. The first is generating the samples that you use in the Monte Carlo. And so this is something where you run a Markov chain and you're collecting a set of representative configurations of the gluon degrees of freedom. And this is something where you really require capability hardware because you're running at hundreds or thousands of GPU scale. Then on those representative samples, you want to compute physics. And this nicely factorizes into a first piece where you compute something called a quark propagator, which basically gives us a probability amplitude for a quark from over here to get over here. And this is something where you're doing very large sparse linear algebra to solve the Dirac equation, a generalization of the Schrodinger equation. We do that many times on each of these sample configurations. And this is somewhere where capacity hardware is kind of more appropriate. You need to do you need to look at these systems many times, but each of them you can run on tens to hundreds of GPUs. And this part of the calculation is actually typically memory bandwidth limited. Finally, in order to construct particular physics observables, you combine those propagator objects in various ways, and this requires high-rank tensor operations. A lot of the time we try and do those in a batch manner. And then finally, there's some offline kind of statistical analysis of the results that we need to do. So some challenges that come up as we go forward really come from trying to do precision calculations. So to be very precise, you need to control the extrapolation to the continuum limit and to infinite volume very well. One thing that happens because our sampling algorithms are essentially quasi-local is that as you try and do that, as you try and take the continuum limit in particular, because physics is at some fixed length scale, and as you're shrinking the discretization, the correlation lengths are becoming very large. You get some kind of critical slowing down in the algorithms here. But this is something where we need to do this in order to get to the precision levels we have from experiment. Also, we need to, when we get to order percent level precision, we need to include the effects of QED and break differences of the up and down quark masses in the theory. And both of these introduce kind of complexities that really change the algorithmic requirements quite substantially. And so there's ongoing developments as how to really push this field to sub 1% precision on many quantities. Kind of at the other end, going to complicated systems, there's, as I mentioned earlier, there are kind of exponentially bad problems that come in here. One of them is to do with, is kind of very similar to electronic structure calculations. The Wick contractions you do in order to form the physics observables basically show a factorial growth as you look at more complicated nuclei. And so a lot of effort has gone into, and it continues to go into, trying to find efficient ways to do these calculations. And I should point out the current state of the art is nuclei of atomic number about 5, whereas in experiment you can access atomic number 250 or so, right? So we have a long way to go. So no sense in which this field is going to stop. I mentioned statistics a little bit before, but quantities that we're particularly interested in, as the field has progressed, we want to look at more challenging quantities, and these are typically more statistically challenging to determine. So nuclei, for example, there's an exponentially bad signal noise problem in calculations of nuclei as you increase the atomic number. Looking at protons that are moving very fast are increasingly noisy, but this is something that we really want to do for understanding their structure. And things where we look at the gluons inside protons and nuclei are also intrinsically noisy. So we need better sampling procedures. And so there are various things that are being explored. They have different algorithmic requirements. So one of them is hierarchical sampling, where different parts of your space-time lattice you're doing very different things with. This is something that requires rethinking how you do the calculations. And there are other ways you can try and improve this. One thing I would point out is that after 40 years of lattice QCD as a field, we've basically reached the point where we are doing calculations that are no longer toy calculations. They really are the things that connect to the physical world. And so the kind of data requirements are changing because the samples that we're producing now, they can be used for physics for decades, potentially, right? They really will be, they will be useful objects to keep around for a long time. So things like HPSS at NERSC are very important for our field, and I think will become more so. We discussed yesterday a lot about modern architectures, and one thing that came up was floating point precision, with machine learning really pushing us towards the minimum possible precision needed for the machine learning applications. And we've seen that in the performance of hardware. So here's a list of some recent and future hardware. And as you can see, the FP16 and FP8 and FP4 performance of these systems is remarkably high compared to the FP64 and FP32. And for example, even for this new AMD system that hasn't come out, but they released some details of it a few days ago, they didn't even bother to tell us what the FP64 or FP32 performance was. And this is something we have to adapt to. This was mentioned yesterday. Also, things have changed in the ratio of compute to memory to network bandwidth, and this is really meant we have to think differently about how to do calculations. So really, in our field, we've using low precision is something that we've really taken to heart, and a lot of the solvers that we use do low precision solves for much of the time and then refine them. And there's also a lot of algorithmic thought going into communication avoiding algorithms. And finally, quantum computing is something that people are thinking about for doing quantum field theory calculations like QCD. From my point of view, it's certainly not obvious that this is where the future lies. Really, I think it's something where there are problems that we can tackle with classical computing. There are problems we can't tackle there, and quantum computing has potentially an advantage there, and that's really where I think it's most sensible to invest the time in our field, at least. And finally, I'd say that these developments are really something that doesn't happen in vacuum. So there's in our field, there's been a strong community framework for developing software, and this has had a lot of support from DOE over the years. And really, that's really what has enabled this connection, this adaptation to modern architectures over time. And so with that, let me finish, and thanks to NERSC for all the flops over the years.